much for inviting me. Thank you very much for coming. I consider the quality of pricing is very proportional to the value of the talk. So I think I consider that the quality of pricing is inversely proportional to the quality of the talk. So I make an effort because I have an appreciation that you can imagine what it is on the quality of my talk. But I hope that you will have another appreciation. So let's begin. A simple remark to begin with. Descartes' geometry, as well as its whole mathematical production, manifests little attention for theorems and mainly focused on problems. This has brought many commentators, for example Henk Bos, to describe Descartes' geometry as mainly concerned with problem solving, and to infer that Descartes' primary aim is in doing geometry was to provide a general method for geometrical problem solving. The description is irrefutable. But is it the same for the inference? I argue that it is not, and I rather reject its consequence. According to my reading, Descartes' primary aim was rather to extend the geometry expounded in the elements, which I shall call for short Euclid's geometry. Better, his aim was to promote a wide-ranging reform of geometry and to suggest a fresh foundation of it, both consistent with and deeply innovative with respect to Euclid. My purpose today is shortly accounting for this reform. My starting point is another remark, namely one concerning Euclid geometry. In Euclid geometry, problems play a crucial role. Solving them results in providing geometry with its own ontology. If the aim was to extend Euclid geometry by extending its ontology to remaining consistent with it, one had then necessarily to suggest new ways for solving problems, resulting in the introduction of new sorts of objects. This was just what Descartes did, in my view. Euclid's geometry was not about a fixed domain of objects, consistently defined and supposed or proved to exist once for all. It was rather, in my mind at least, about some sort of transient objects available by license and constructions. To appreciate the difference, remark firstly that to be available is a modal verb. A certain X being available is not its being there, or its being so and so. It is rather its being able to be obtained. What I mean then by saying that a sort of object is available by the essential construction is that one or more objects of this sort can be obtained by these constructions. Hence, the first part of my claim is that Euclid geometry was about objects that could be obtained by licensed constructions. The second part pertains to the adjective transient. What I mean by it is that once obtained, the objects of Euclid geometry is about are not kept in stock. Better, they are neither ascribed to a cumulative totality to be referred to or considered as such, nor are they stored for future uses. Kept attention. Here I am speaking of objects, not of sorts of objects. What I said concerns single objects of a certain sort, not sorts of objects. For instance, single triangular squares, and neither the triangles or the square as such, nor some triangles or some squares, so and so. What a licensed construction allows obtaining are single objects of a given sort. A single triangle or a single square, for example. And what are transient are just these single objects. More than that, typically, once some assumptions are made at the beginning of a construction relative to objects which are licensed to be obtained at the zero step of the construction, these single objects are determined as such. They are neither arbitrary or generic triangles or squares, not arbitrary or generic triangles or squares, so and so. They are those determinate square and triangles. But then, why did I say that Euclid's geometry was about some sort transient objects. Here comes the third part of my claim. Truth what a Lysenko construction allows one to obtain are single objects and they are transient. What is relevant for Euclidean geometry is generality. And generality cannot depend on the act of obtaining single transient objects. It rather depends on the possibility of obtaining single transient objects of a certain sort. That is, not on some single object of that sort having been transiently constructed, but on the permanent availability of that sort of objects, on the fact that they are permanently able to be constructed. The relevant questions for Euclidean geometry are then the following. Which sort of objects are available by Lysenko constructions? That is, which sort of objects can be obtained by such a construction? And how this sort of objects are exactly? That is, how the objects so obtained actually are, besides being the object of the relevant sort. Solving problems allows one to respond to the former question. Proving theorems allows one to respond to the latter question. But responding none of this question requires the single object obtained are permanent, that is, are kept in stock once obtained. It does not require that these objects are ascribed to a cumulative totality to be referred to or considered as such, since generality does not concern the totality of objects, either fixed or cumulative. It rather concerns availability, that is, possibility of obtaining. It does not require these objects are stored for further uses, since if a certain sort of object is available, an object of this sort can be obtained any time this is required. It follows that for the solution of a problem to be able to respond to the question it is required to respond, there is no need to ensure any sort of permanent existence to any object or sort of object. Solving a problem has merely to show that the object of the relevant sort are available, that is, that this is a sort of available object. It does it by actually constructing a single object of this sort. Still, what is relevant here is not whatsoever construction. The point is whether the relevant sort of object is available by a Lysenko construction. Fixing which are the Lysenko construction accomplished with a double purpose. Provided that this is made in an appropriate way, as it is in Euclidean geometry, it is ensured that the construction is repeatable, with the result that constructing a single object provides a suitable response for the general question about availability mentioned above. This also contributes to make Euclidean geometry is a closed theory, that is a deductive system with sharp limits fixed by its language, its basic assumptions, and its rules. No need to say that Lysenko constructions in Euclidean geometry are construction by rule and compass. What is needed instead is to remember that Euclid never describes these constructions this way. Describing them this way is rather part of Descartes' way to think. To avoid explanatory circularity, let's then call them, for the time being, elementary constructions. They are the construction licensed by postulates 1, 3 of the elements, plus a number of other clauses, either tacit or only implicitly stated. Extending Euclid's geometry by extending its histology to remaining consistent with it require then to license further construction besides elementary ones, which would have resulted indeed in making further sort of objects are available besides those available in Euclid's geometry. This is just what Descartes suggested to do, according to my reading. Still, this could have been done in many different ways. Broadly speaking, the question of how doing it in an appropriate way was just the problem of geometrical exactness afterwards. The first important distinction to be made is between local extensions and global organic ones. A local extension of the geometry of Euclid's geometry would have merely allowed one making available some particular sort of object. By making some particular sort of problem unsolvable, Euclid geometry becomes solvable. A global organic extension would have resulted in a new theory larger than Euclid's geometry, but equally closed in its being as well, a deductive system with sharp limits fixed by its language, its basic assumption, its rules. By saying that Descartes aimed at a wide-ranging reform of geometry and suggested a fresh foundation of it, I mean that he pursued such a global organic extension of Euclid's geometry. To appreciate his suggestion, we need to look at two other things before. How problem works in Euclid geometry, or better, what does it mean more exactly that solving a problem shows that the objects of a certain sort are available, and what was the state of geometry to Descartes' eyes, or better, how the mathematician before Descartes tried to respond to the question of geometrical exactness. I'll try to shortly look at them now. Looking at the former requires to distinguish two quite a different way of specifying a certain sort of object using the language of Euclid geometry. The first way provides an intrinsic specification of the relevant object considered per se. It generally results from a definition explicitly signaled or a specification of it, saying that an object is an object of a certain sort in this sense, resulting in saying that it is a point, a segment, a circle, an angle, obtuse acute or right one, or rectilinear or horn, a circle, a polygon of a certain kind. The second way provides an extrinsic specification of objects already specified in the first way, relatively to other such objects. It depends on fixing some appropriate relations that the relevant objects specified in the first way are required to stay with other such objects, saying that an object is an object of a certain sort in this second sense, resulting in saying, for example, that it is a point cutting a given segment of extreme angular ratio, or a square equal to a given triangle, or to a given circle. For short, I call an object unconditional, insofar its sort is specified in the former way, and conditional, insofar its sort is specified in the latter way. In this liberal parlance, a triangle, or also an equilateral or right-angled one, is an unconditional object, whereas a right-angled triangle having an equal to a certain acute given angles is a conditional object. Of course, for an object to be unconditional or conditional is then not to be as such so-and-so, but to be regarded as being a so-and-so. In other terms, the distinction concerns our description of the relevant objects, not their mode of being. Let me now introduce a further terminological combination. I call E objects, for Euclid's objects, either unconditional points, segment, circle, angles, and polygons of any kind, or conditional such objects specified in the language of Euclidean geometry relatively to other such objects only. In short, an E object is then an object that Euclid's geometry is concerned with. Any unconditional E object can be defined in the language of this geometry, but some sort of unconditional objects that can be so described are not E objects. For example, ellipses can be described in the language of Euclidean geometry, but are not objects that Euclid geometry is about. What is more relevant is not this, however, but rather that not any sort of unconditional E objects is available within Euclid geometry, that is by an elementary construction. For example, heptagons are not. Moreover, showing that a sort of unconditional E object is available within Euclid geometry can be far from simple. For example, proving that is the case for heptadecagons with 17 sides is quite complex and was first proved only by Gauss. The first crucial purpose of solving problems in Euclid geometry was to prove that a certain sort of unconditional E object is available within Euclid geometry. The solution of proposition 1-1 show, for example, that is the case for equilateral triangles. For conditional E object, the dyscrasia is even more evident. Any conditional E-object can be defined in the language of Euclid geometry. But many sorts of conditional E-objects are not available within Euclid geometry. For example, angle intersecting a given rectilinear angle, or squares equal to a given circle are not. Another crucial purpose of solving problems in Euclid geometry was to prove that a certain sort of conditional E-object is available within Euclid geometry. That is, each such object is obtainable by elementary construction from the object relative to which it is specified. A solution of problem 1-2 shows, for example, that segments equal to given ones and having one of their extremity in a given point are available. So, these are the two things that you make in Euclid geometry, to prove that certain sort of unconditional objects are available, for example, the equilateral triangle, and another thing is to prove that certain sort of conditional objects are available, for example, that you construct a point that cut a segment in a certain way. I come now to the second thing to look at before describing the Cartesian field. Euclid geometry is far from exhausting pre-Cartesian and even Greek geometry. Still, with the only possible partial exception of Apollonius' theory of conics, no other portion of pre-Cartesian geometry looked like it. That is, as closed organic theory. Going further than Euclid geometry was to enter a much more sleeping area. Moving in this area required looking for non-elementary constructions. But non-elementary construction of what? Firstly, one was merely looking for non-elementary construction of E-objects non-available within Euclid's geometry. For example, angle intersecting given angles. Secondly, one was looking for non-elementary construction suitable for making available some sort of geometrical object other than E-objects. For example, curves other than circles, conics. The most part of these latter objects were defined by describing possible construction of them. Admitting this construction came then ipso facto together with warranting for their availability. Hence, the general question there was less that of looking for new sort of construction than that of deciding whether this construction were right. A natural way for looking at this question was to wonder whether admitting this construction and taking then the corresponding object to be available could have allowed to construct in a particular suitable way E-object non-available within Euclid geometry. From this topic, optic, what became relevant was then looking for sort of non-elementary construction allowing to obtain these objects. Asking for obtaining an E-object non-available within Euclid geometry by a non-elementary construction was to state what I call a quasi-Euclidean problem. Understanding the Descartes form is merely helped by looking at the different ways suggested for solving quasi-Euclidean problems. The angle intersecting the two mean proportional and the circle squaring problem were three classical problems of this sort. I have no time to give examples. Being many of the solution advances for this problem quite well known, resents me in asking you to think to them alone. Please. I merely offer a classification of the different constructions suggested by solving this problem before Descartes in 6 families. First come to family of what I call quasi-elementary constructions. Construction relying only on E-objects to applying constructive clause not included among those of elementary construction. The first family includes construction using some instruments for getting some points under the condition that some element of these instruments coincide with some given geometrical object or meet some other condition relative to given objects. In my parlance, these are constructions using mechanical instrument in the pointing way. You look there if there is a coincidence. Okay, here. The second family includes construction appealing to some explicit stipulation of tacit admissions, working as a new constructive clauses, like yet, noises, postulate. Then come 4 families of what I call strictly non-elementary construction. Construction relying on some object other than E-objects, namely some curves other than circles. They differ to each other for the way these curves are obtained. The first family includes construction involving conics, which are supposed to be ipso facto obtained for being univocally determined. The second includes construction involving curves traced by instrument used to trace them. That is, as I say, in the tracing way, instrument used in the tracing way. The third includes construction involving logic, obtained by constructing a generic point of them under the supposition that their generic point is given. And the fourth, include construction involving curves obtained by interpolation. Now I can come to Descartes. A rapid way to describe Descartes' reform is by accounting for his attitude with respect to non-elementary constructions. The first thing to be said is that his aim was not merely to accept some of them while rejecting the others by relying on some good reasons. It was rather to integrate some of them within a closed theory extending Euclid geometry and being so close and organic as it. In other terms, what he was looking for was not some scattered sort of assimilable non-elementary construction, but a unitary extension of the norms of elementary constructions. A unique principle to be used to sense a unique sort of construction, including elementary ones, but more than that. This unique sort of construction should have, moreover, been comprehensive enough to allow the solution of the most part opposed trivial problems. This sort of unique construction is what I call constructions by ruler, compass, and reiteration. The basic idea is this. Admitting that E objects available in Euclid geometry are also available in the same sense in the extended geometry. Using elementary construction to obtain a configuration of single such object to be conceived as moving consideration, such that a line is traced by moving them. Then consider curves traced in this way to be available in the extended geometry and appealing to other elementary constructions, only extended by integrating in them single curve like this, to obtain a new configuration of single available object to be used like the previous one, and continue this way indefinitely by obtaining a new sort of curves, all available in the standard geometry, and new configurations of single available object to be used to trace other curves. So the idea is essentially, according to me, use construction by rule and compass to construct instruments for constructing other things that are not objects constructed by rule and compass. So this is the idea of reiteration. I call a moving configuration of single available object obtained in this way a geometric linkage. My basic point is then that Descartes' compasses are geometrical linkages. This entails that these compasses are to be regarded as geometric objects in turn, and are then available in the extended geometry in the same sense as E object can be so in Euclid geometry. They are not mechanical instruments, they are geometrical objects. Still, for they to be appropriate for entering a construction by rule and compass of their iteration, they have to be such that a unique curve can be traced by moving them. This curve being determined by the nature of the linkage itself, and not also by the way as it is moved. In other terms, geometrical linkages are not to be variably moved by human hands or other forces, but merely be conceived as movable and univocally determining a single curve. This is just what happened with usual compasses with a fixed angle. And it is just what they make, and the curve they trace are geometric. I usually make this example. You take a compass, you begin to make a circle, then in the half of them you go, okay, I go to take a coffee. You go to take a coffee, you come back, you continue the circle. The circle is exactly the same that if you had constructed in the same way. So the motion of the compass is not essential there. Simply the conception of the motion that is essential, but the actual motion is not there. The speed in which you make the circle are absolutely not relevant. And this is exactly the point of Descartes compasses. If you want to construct a spiral with a segment that turn around and in the same time go this way, There, the speed is essential. The actual way in which the motion is performed is essential for the result. So there are instruments of two sorts. One instrument for which the motion is not essential, or simply the conception of the motion is it, and other instruments where the motion is essential. The first are geometrical, the second mechanics. This is the idea that I have. Hence, geometrical linkages entering construction by ruler, compass, and reiteration are natural extensions of usual Euclidean compass. Just like E-object, these linkages can be either unconditional or conditional. Conditional ones are available if they are constructed by ruler, compass, and reiteration, starting from the object with respect to which they are specified, which are in turn available. They are required for tracing conditional available curve in appropriate position, which is required both to solve quasi-Euclidean problems and to trace other conditional available curves, are just required by construction by ruler, compass, and reiteration. If you wanted to solve the problem of two means proportional using a curve described by the compass of Descartes, you don't need simply the curve, you need the curve in a certain position. So you have to know that you can construct not the curve in general, but the curve there. And this is something that I call a conditional compass. Compass that can construct the curve there. Many other details and specifications could be given and many examples offered. But the little I have said should be enough to make clear how Euclid geometry, namely its ontology, is extended by license into construction by ruler, compass, and reiteration. This is all what I wanted to explain. I can then conclude by saying what was, according to me, Descartes' attitude with respect to the 6 families of non-elementary construction considered above. The first point is that Descartes rejected quasi-elementary construction from the very beginning. I remember quasi-elementary construction in parlance as construction that use only Euclidean objects, but with clauses that are not Euclidean clauses. For example, you simply construct points, but in order to construct this point, you use a certain instruments in the pointed way. If, for example, a Toscanes solution of the two-mean proportional problem, you use the mesolabum in a certain way, you open, you close, you see, you look, there is a constant, so here is the point that you want to construct. There you construct simply points. There is no object that is not Euclidean in the construction, but simply the point is constructed in a way that is not the way that Euclid geometry allows. So Descartes rejects this sort of construction from the very beginning, unless, of course, they could be recast under the form of another sort of deceptive construction. The reason seems to have been the following. Those based on stipulations, like the noises postulate, seem to be rejected, for this very stipulation were considered merely ad hoc. Those relying on instruments using the pointing way seems to be rejected, since this is a more complicated point. This use of instruments were considered to this use of sorry, there is a mistake in English, so I read it in a good way. This use of instruments were considered very different for the use of this use of instrument were considered to involve using this instrument and geometrical diagrams in a way that essentially differ for the way diagrams enter both elementary constructions and construction by ruler, compass, and reiteration. The difference pertains to this. Using instrument in the pointing way allows to obtain the points constructed through them only if one looks at them as physical objects having some mutual position to be recognized by inspection. Whereas geometrical linkages are geometrical objects merely represented by diagrams, and this diagram, just like those representing E-objects in geometry, enter the game only for the condition they are forced to meet, not for those they are recognized to meet by physical inspection. If I have 2 minutes more, I perhaps make... In the Euclid geometry, you never solve a problem in this way. I wanted to know, for example, if this segment is equal to this one, so I take a circle here, and then I look there, look, is it exactly there or is not there? Can I see? Yes, perhaps it's not, so it's not equal. Ah, look, it's exactly there, so it's equal. Never this way. If the circle pass here, simply if this is equal. It's not equal because the point, the circle pass there. Or if I want to see that this is equal to this because the point pass there, I have The point was there, not because I see it, because I force it, because of geometrical reason for it. If you take a Eratosthenes Mesolabium to resolve the problem of two mean proportional, you have to move in that and to arrive in a certain situation which is, and there is a curve here normally, is coincide exactly with that. So you look at the diagram in a certain way, and you say that the solution of the problem is given by the fact that you expect the diagram. This is never what happens in Euclid geometry. So my idea is that Descartes reject this sort of construction simply because they are in spirit what Euclidean. So this is for the two families. Now concerning strictly non-elementary construction, the situation is as follows. Construction involving univocally determined conic were directly recast as construction involving curves traced by geometrical linkages, because conics are traced by geometrical linkages, so no problem. Since conic can be so traced, so they are simply part of the system, no problem, they are accepted. Construction involving curves traced by instrument using the traced way were directly recast as construction involving curves traced by geometrical linkages, if the relevant instrument can be recast as such a linkage. Otherwise, they are rejected. This is also the case for construction involving loci, obtaining by constructing a geometrical point of them. In many cases, indeed, this loci can be constructed by recast, as curve traced by geometrical linkages, whose construction is directly suggested by the construction of this point. What means if you look at the way the loci are constructed, this way suggests a way to construct a geometrical linkage. So simply you have to take the suggestion to construct the linkage, and this is done. The situation is different for construction involving curves obtained by interpolation. The construction of this point provides no suggestion for constructing geometrical linkage to be used to trace these curves. The case of interpolation, for example, the case of Clavio construction of the quadrantries. You construct the middle point and then the fourth here, but you construct an infinite number of points, but not all the points. And as you do not construct all the points, or you do not construct a generic point, but you construct a specified point, the construct this point, they give no suggestion about the way of constructing the linkage. So you cannot accept that. Hence, this construction were rejected unless it is not independently shown how to obtain the relevant curves to the construction by Wood and compass and derivation. Okay. On the second of these cases, it is perhaps useful to say that Descartes accepted construction involving curves traced by instruments presenting strings, if and only if these instruments can in turn be recast, mutually mutatis mutandis as geometrical linkages. This generally happens if the physical nature of the strings is not essential for the instrument to work. I finished. Which happens instead, for example, with Huygens' instrument for tracing spirals, which was then rejected. To complete the account of Descartes' reform, one should, of course, besides adding a lot of details, explaining as curves traced by geometrical linkages were regarded as geometrical curves and connect to polynomial equation. I suppose that Andy will explain this in his talk in the next meeting, more or less. Certainly in a way that I do not agree with, but this is not a problem, it's another question. And our choice was made among different possible solutions by ruler, compass, and reiteration of the same problem on the basis of a criterion of algebraic simplicity. This is something that I cannot do here, however. My aim was only to show, as Descartes geometry directly stems from extending Euclid once. The introduction of equation was, in my view, a posterior step, made possible by this extension. This is the strong claim that I make is exactly this. Algebra comes before. You need before. After that, you need a reform of geometry. And it is because of the reform of geometry that you can apply algebra. It's not the application of algebra, or better, what I want to say, the algebraic formalism, because it not consider that algebra was a separate discipline in this period. So it's only because of this reform of geometry that you can apply the geometrical formalism, not vice versa. So the motion, the reason of the changement is not in the algebraic formalism. The algebraic formalism is the result of the radical reform, not the cause. The introduction of equation was, in my view, a posterior step made possible by this extension. A step that suggested along the next 2 centuries the path to be followed for getting an essentially different geometry based on a structurally different ontology. But it is another story to be told another time. if you will invite me again. So for the time being, obrigado.